So this is the basic circuit diagram for the microwave transmitter, very simplified of course. In looking at the circuit diagrams for the transmitter, you can break this down into three basic power supplies. You have an anode supply, which is made up of the plate transformer, which is 111 kVA or 106 kVA, depends on the model transmitter. You have a filament power supply, which is essentially just a transformer and a rheostat. In some cases, there's an electronic controller for the filament current rather than the electromechanical device. And then we have the solenoid power supply, which is comprised of a power stat, a choke, a diode bridge, and some filters. And then all of this connects to the magnetron tube, which is here. Now, what's interesting to note about the plate supply is that the positive side of this is actually grounded. The tube is mounted into the anode of the tube is the positive element. That's the case of all tubes, magnetrons or otherwise. The way this tube is made, the anode is the outside of the tube, and the water jacket, everything's all connected, and it's grounded by the mounting hardware when you put it into the transition and then down into the solenoid. So the positive is essentially the ground, the whole cabinet, everything is the positive sort of side of the plate supply. The negative supply has the high voltage wire that comes off of your diode panel, rectifier panel, and connects to the filament, the stem of the tube, and the filament transformer wires. So it's actually minus 18 kV, that's the active element that you got to watch for when if you happen to open the transmitter when it's running. So the combination of the anode supply and the filament supply and power stat, or the solenoid supply, is how we control the tube. The filament has to be at 2100 degrees to get the proper emission, and in standby, when we're not radiating any RF, that's 115 amps at approximately 12 volts. That's derived here. And to control the RF output, we vary the solenoid current, which affects the magnetic field strength and adjusts the output power. If the solenoid current is high enough and therefore the magnetic field is strong enough, we can stop the oscillation safely and entirely and hold the tube cut off, so to speak, and that happens at about 4.9 or 5 amps of solenoid current, and that's what we call the standby mode, and we can activate the high voltage and apply the minus 18,000 volts without getting any RF power. When we want RF power, we move the power stat down a little bit, and it reduces the solenoid current, and the RF power will it'll start oscillating, and we'll get RF power, and so the more we reduce the solenoid current, the more RF power we get, within reason. The tube has safe limits, of course. Now, one of the other interesting things about how magnetrons work is that when they're radiating, there's the electrons come off of the filament and fly around in the tube, do their thing, and some of them come back and hit the filament again, and they cause it to get hotter because they release energy. The electrons release some energy into the filament. So we have to account for that and prevent the filament from getting too hot, and that's done via what we call a cutback, where we intentionally reduce the filament current in the filament supply in conjunction with decreasing the solenoid current to increase the power. So in the older machines, there's a rheostat, which is motorized. It's actually chain driven by the motor that runs the electric power stat, and so they move together. So as you raise the power, they both move, and we get a power increase on the RF output, and the filament cutback is taken care of by the mechanism. So at full power, at 75 kilowatts, you get about 82 amps of filament current. But the filament itself doesn't cool off because it's being heated by the back heating, or the back bombardment of all these electrons. When the cutback is set up correctly, filament temperature is essentially constant at all RF power levels, and the tube will operate reliably and have long life under those conditions. So it's important to make sure that the cutback is correct, so that the tube will operate safely and have a long life. So you'll also notice that we have quite a bit of circuitry here. The solenoid is represented here, and there's a couple of diodes and a capacitor that are parallel to the solenoid, and these are kind of swamp the solenoid. Sometimes they're called flyback diodes, and what that is for is to protect the solenoid itself and the external circuitry from a high voltage pulse if the solenoid power is shut off unexpectedly, like if the whole machine is kicked out from a breaker opening somewhere. Because the magnetic field that's generated there will collapse around the coil, which the solenoid is basically just a large coil of wire, and in that case it will induce a large voltage, which is in the opposite polarity of the normal running voltage. And so these diodes and the capacitor absorb that energy and dissipate it safely without injuring the other components. And you'll also see that we have an anode current meter here and solenoid current meter here. Some transmitters, these aren't actual panel meters, sometimes they're a shunt that goes and drives a PLC input or something like that, but they're in the same locations. So the anode current meter is in series with the the positive side of the plate supply and represents the anode current. The solenoid current meter is in series with just the solenoid supply. So this goes to ground and it actually returns up here. So this one is isolated from the anode current so that they represent their respective currents correctly. Now you'll also notice that the anode supply, the anode current, goes through the solenoid, and this is done to create a feedback circuit that helps stabilize the power output. So as we increase the RF power and the anode current rises, it generates an additional magnetic field in the solenoid, which is contrary to our reduction of the solenoid current to increase the power. And that means that as the RF power goes up, it will attempt to reduce the RF power. And that purpose for this is so that if the power mains in your building fluctuate from other large machinery turning on or off or some other perturbation that would tend to affect the RF power, this feedback circuit will effectively minimize that power fluctuation. So, and you may notice that at full power you have 5 amps or 5.2 amps of anode current, and that would normally be enough to shut off the oscillation. So to make sure that we don't get too much magnetic field from the anode current, we bypass part of it through this 50 ohm resistor. Most of the transmitters, this is an adjustable part that's set to about 40 ohms. Each transmitter model is a little bit different. In the older 30 kilowatt units, it probably doesn't have this at all. 50 kilowatt transmitters, it's like maybe 75 ohms or something. As the power level went up, this value has to reduce so that you bypass more and more of the anode current so that you don't cut off the tube with the anode current itself. So if you didn't have this, basically what would happen is you'd shut off the solenoid supply and the tube and the output would run at 30 or 40 kilowatts or something like that. You'd never make it to 75 kilowatts, it would kind of self-regulate. So we swamp or bypass some of that current here. And so the solenoid supply is fairly simple. It's just driven by the power line through your control transformer. There's a choke here which limits the current, sort of like a ballast, and then there's a diode bridge, filter capacitor, and then goes into the line that feeds the solenoid here. And this diode is here to isolate the anode current, and this diode isolates as well. So the two currents can feed together, and some here, and then go through the solenoid to ground. But neither of them can backfeed into the other circuit. So your anode current's not going to drive this, and that other one's not going to drive that. So it's important for these obviously to be here and to be in good condition. And it's one of the failures that occurs sometimes when the tube sparks. It can draw more current than these diodes can handle, and it'll short them, or perhaps they'll open, but that's a little bit less common when one of these shorts circuit doesn't work correctly. So you got to make sure to check that when you're troubleshooting a problem. Let's see. Where did you kill for a minute?